Assalamualaikum and hello. Today we will present a chapter from Strength of Material where the course code is DJJ 30103 and our lecturer name is Sir Alias. Our group member is me, Muhammad Iqbal bin Zamri, 24 DKM 22F 1023, and then we have Muhammad Hafizuddin bin Muhammad Zaid, 24 DKM 22F 1053. Then we have Fatur Rahman bin Fauzan, 24 DKM 22F 1008. And lastly we have Alia Kristina binti Abdul Rahim, 24 DKM 22F 1002, where we are all from DKM 3A. So for the next slide we have table of content, where we start off with introduction. Then 6.1 classify the type of shaft. For the subtopic is 6.1.1 torsion equation. 6.1.2 relationship between shear stress and torque. 6.1.3 the second polar moment of area. 6.1.4 series and parallel compound shaft. And lastly we have 6.1.5 power transmitted by the shaft. For the introduction, torsion is the stress produced in an object when it's twisted. The amount of force that twists the object is measured in torque. When an object is twisted beyond its limit, it will break. According to Hooke's law, for linear elastic material, shear stresses are proportional to shear strain, and constant of proportionality is the modulus of rigidity.
6.1 is classify the types of shaft. There are three types for the shaft. The first one is a single shaft. The second one is series compound shaft, and the third one is parallel compound shaft. 6.1.1 torsion equation, where the equation is PA over R equals to G theta over L equals to T over J, whereas PA is shear stress, and R is radius in meter. G is modulus of rigidity. The theta is the angle of the twist. L for length in meter, and J for polar second. 6.1.2 the relationship between shear stress and torque. To determine the relationship between applied force torque T and the stress it produces, we consider the equilibrium of the internal force and the externally applied torque T, considering an element area D times A within an element ring of thickness dr situated at radius r from the center.
For the 9.1.3, the second polar moment of area. The polar moment of inertia, also known as the second polar moment of area, J, is equality used to describe resistance to torsional deformation in cylindrical object with an invariant cross section and significant warping or out of plate deformation. So the formula for solid shaft, J equals to integrate 0 from 0 to D over 2 pi x cube dx. So we have to integrate the formula, the original equation. So it will be J equals to pi D power of 4 over 32. So for the tubular shaft or hollow shaft, the original equation is J equals to integrate D over 2 to D over 2 pi x cube dx. So it will be J equals to pi over 32 times D power of 4 minus D power of 4. For the 6.1.4 series and parallel component shaft, for the series component shaft, when the two similar or dissimilar shafts of the same or of different material are connected together to from one composite shaft, driving torque being applied at one end and the resisting torque at the other, the shafts are said to be connected in series. Consider each component shaft separately, applying the torsion theory to each in turn. The composite shaft will therefore be as weak as its weakest component. For the formula of series component shaft, the formula for the torsion TAC equals to TAB equals to TBC. For the angle of twist, theta AC equals to theta AB plus theta BC. For the parallel component shaft, consider as parallel component shaft because fixed at both ends. Another parallel component shaft, if the driving torque is applied at the junction of the two shafts connected together and the resisting torque at the other end of the two shafts, then the shafts are said to be connected in parallel. The torque applied in this case is divided between the two shafts, but the angle of twist is the same for each shaft. For the formula of parallel component shaft, formula for torsion TAC equals to TAB plus TBC. For the angle of twist, theta AC equals to theta AB equals to theta BC. So this is the example of shaft in series and the shaft in parallel. We can see the top one is a series and the bottom one is parallel.
Power transmitted by the shaft. Let us suppose that a motor driven shaft in figure 6.1.2 is rotated at an angular speed measured in radians per second. The shaft transmits a torque to a device that is performing useful work. The torque applied by the shaft to the external device has the same sense as the angular speed. This is it. Vector point to the left. The formula is P equal to T W equal to pi Newton over 60. Example question. A. State the terms and unit for each symbol below. G theta over L equal to T over J. The answer is T is torque, Newton meter. G is modulus of rigidity, Newton per meter second. Theta is angle of twist, radians. R is radius of shaft, meter. L is length, meter. C is polar second moment of area and power form. Last, T is shear stress, Newton per meter second. A copper shaft has a diameter of 55mm and 65 cm. Long is having applied torque of 2.85 kN per meter. Express the value of shear stress and twist angle of the shaft through to apply torque if G copper equal to 40 kN per meter second. The answer is, first step, G equal to pi T power 4 over 32 equal to pi bracket 55 multiply 10 power negative 3 bracket power 4 equal to 8.894 multiply 10 power negative 7 meter power 4. The second step, T equal to TR over J equal to 850 bracket to 7.5 multiply 10 power negative 3 bracket over 8.8984 multiply 10 power negative 7 bracket equal 87.238 multiply 10 power 6 Newton meter per second. Last step, theta equal to TL over JG equal to 850 multiply 0.65 over bracket 8.984 multiply 10 power negative 7 multiply 14 multiply 10 power 9 bracket equal 51.55 multiply 10 power negative 3 radians.